Good afternoon, everyone. Thank you for attending our Custom Battery Pack Design Considerations for Performance and Safety webinar. My name is Ryan Wood, the Content Marketing Manager here at Epec. Before we get started, I just want to let you know that you'll be muted during the presentation. If you have any questions as we move along, please enter them into the questions panel, which is located in the webinar control panel, and we'll try to get to all of them at the end of the presentation. If we don't have time to go through all your questions, we'll be sure to reply to you by email. Also, we'll be recording this webinar and posting both the recording and the slides on our website and the video on our YouTube channel. Our presenter today is Anton Beck, our battery product manager. Anton came to Epec with over 25 years of electronics manufacturing experience. His background includes all manufacturing processes from design to fabrication. He's consistently focused on developing our battery design and manufacturing infrastructure to continually improve our value-added supply chain organization. Anton's responsibilities include overseeing our design team, product and prototype development, tooling and test processes, regulatory approval management, and subcomponent supply chain to ensure Epec's world-class standards to our customers are maintained. And Anton oversees hundreds of custom battery pack designs, and he has extensive experience with medical devices, certifications, and military power electronics applications. But without further ado, I'll now pass it on over to Anton.
Well, thanks, Ryan. So good afternoon, everyone, and thanks for joining our webinar. Today, we're going to discuss some considerations when designing a custom battery pack. Our agenda for today is going to be understanding some design factors, optimizing performance for certain applications, safety and reliability, and we have a few case studies that we've done at Epec that we want to share as well. So understanding the key battery pack design factors. The first important element would be determining the cell to use. There are several options, so depending on the device requirements and spacing available, you'll need to select a cell that can deliver the power or energy you're targeting. These could be lithium-ion, lithium iron phosphate, nickel metal hydride, etc. And as you can see, they come in different form factors, so you'd have to determine which is best for your application. Let's discuss some optimizing and performance. You also have to calculate voltage and capacity needed to determine what's going to be required for the cell configuration. Cycle life is typically determined by the cell specifications, but you can extend with lower charge or higher discharge cutoff settings to use in the battery pack with a less extreme cycle. Temperature also plays a key role in the life of the battery, so the slower you charge and discharge, the less heat is generated, which would typically reduce the life of the battery. Many times the battery selected may be overrated for the application, if there's physical room that is, so that the battery can be used in these less extreme charge and discharge parameters. As mentioned in the first slide, BMS battery management system, will play a very important role in the performance and cycle lives of the battery. There are options for cell balancing, being active or passive, passive being the most common for things like consumer electronics, power tools, etc. Passive balancing is the most cost-effective, reliable, and sufficient for many applications where small imbalances are tolerable or the pack replacement is routine. It works by bleeding excess energy from higher voltage cells, usually as heat, through resistors during or after charging. This helps align voltages across all cells without transferring energy between them. Additionally, BMS features like the protection settings can be customized to improve the cycle life, monitor temperature, and provide state of charge. And as previously discussed, how the selected cell models are configured to meet the performance needed include some considerations for peak and continuous current requirements, as well as what type of fuse and circuit protection that's going to be applied. Connectors and wiring will also need to be factored in to rate the proper gauge for the appropriate capacity, avoid voltage drops and resistance, Additionally, you'll need to be sure that the connector is rated for the voltage intended. It may be a bit redundant topic, but thermal management of the battery is a critical factor in the life of the battery. There are a few ways to manage this. The first being how fast the battery will be charged and discharged, which, as previously discussed, can be customized on the BMS. Temperature sensors can be added. Additional physical cooling might be an option if applicable, or even venting with the battery enclosure itself. And in the mechanical, if the battery requires an enclosure, there's many options such as steel, aluminum, or several blends of plastics depending on the battery size, weight, or IP rating that's going to be required. The enclosure needs to be designed to support the battery through shock and vibe testing, be strong enough not to break when performing drop tests, which are part of the consumer safety testing, and some may require IP ratings to protect from water and dust ingress. The enclosures are designed on the interior to ensure they hold the battery cells and the electronics in place, as well as the outer shell to meet the customer's aesthetics. Let's touch on some safety and reliability. Depending on the markets intended to support, the battery may require additional redundant safety features with fail-safe design principles. This is mostly required in medical field, so customers need to research intended targeted markets as part of the development plan to be able to design to whatever standards or certifications that may apply. There are several layers of redundant fail-safe features, such as overtemp, overcharge, overcurrent, short circuit, and cell balancing, to name a few. Redundant fail-safes are standard in UL 2054, IE 62133, automotive, and aerospace certified battery packs. Life cycle and reliability. Keep in mind, in addition to customizing the battery BMS for optimal performance and cycle life, there are other factors that will come into play on this, such as calendar life, how well the battery charge was managed, and if it was placed in long-term storage. In the environment, of course, it will be exposed to extreme heat in storage or usage will shorten the performance and overall life of the battery. How the battery is designed to be assembled is important for ease of manufacturing, the charge of maintenance previously mentioned, and how the battery is intended to be replaced at the end of its life. Barcoding is a very common practice to have records of when the battery was assembled, how long it's been in use, and even how many cycles it's gone through. This has become a standard practice with most assemblers. Last but certainly not least would be the cell model considerations for availability, lead time, and longevity. Some cell models are not commonly used in larger industries, and the manufacturers may phase them out if they're not popular. Component costs and availability follow the same considerations. IC should be researched to determine an appropriate and market-stable model when you design your BMS. We have seen shortages, extremely long lead times, and some being discontinued. Working with a supplier versus distributor is a good way to review all the details we've outlined and design a custom battery that will perform as required, have the best design practices, and support the life of the project. Now let's review a couple of case studies we've done at Epec. So the first case study was a battery for a portable medical blood fluid warmer. The challenge was the customer needed somebody to redesign a portable, something portable, lightweight, and have more power from a current sealed lead acid model, which was too heavy and not powerful enough. So using our in-house product development and engineering, we worked with the customer to jointly develop the specifications for the new battery. And because this was new, we were able to incorporate new technology and recommend more features that were designed into the product. There's a picture of the battery on the right. So we produced the whole product from start to finish, including internal components and the external plastic. That took a bit. We did it in 6 weeks to complete prototypes, which is a pretty fast pace. And we managed all the testing and certifications to include the UN and the UL. As a result, from start to finish, the internal battery, we managed internal battery intelligence, the plastic enclosure, including the ultrasonic welding process, which we do in-house, custom labeling to meet the customer's product aesthetics, and they were pretty robust labels. And we designed a custom fuel gauge membrane switch to be compatible with that battery. The second case study we have to offer was a portable X-ray machine. And the challenge was to make a lithium battery for a current plug-in AC version, and this could be mobile. And then the battery needed to provide a lot of power. It was limited on dimensional size because it had to fit within a product that they've already developed, and we had to meet the target charging times, which were pretty aggressive. There's a picture of the internals of that battery. First step we did was to provide a customer with a work and engineer samples so that they could launch at a trade show. We also managed this one in 6 weeks and met their timelines. The device was demonstrated with a lot of interest. We then completed the plastic with the customer's team to create the internal design of that case to hold the cells and the electronics. The battery case requirements needed to be compatible and incorporate that interface and fuel gauging features and pass all required transportation and safety testing. That was a moderately heavy battery, so the enclosure had to be pretty robust. So we completed this one. Complete was in 8 weeks. Once again, we met the customer timeline. We then had to build a 50-piece lot to assemble and test for like a beta testing for them. And we managed the UN regulatory. The customer was provided with additional samples out of that 50-piece for the pilot run, and everything went well. As a result, with most battery packs, it's not common to knock it out of the park the first go around. Usually there's a couple iterations of the battery with some tweaks in the electronics. But with understanding the customer's objectives and timelines, we were able to define that scope of work and minimize the need for design revisions. We aced it the first time around. We collaborated on the internal design of the enclosure because we knew what had to be met for regulatory requirements. We also designed the product labels for the customer. Again, those were pretty sophisticated labels. And we managed the regulatory testing and the production's underway. That's the second one. So in summarizing the case studies, ones we did, designing a custom battery pack requires balancing the performance, the safety, using the right cells, formatting it, the right system integrations, good BMS, thermal and mechanical designs that are in compliance with safety standards, which we have experience with, so we did pretty well with that. And make it smart manufacturing so that you understand your supply chain planning and scalability. Real-world case studies highlight how collaboration and engineering expertise turn these considerations into high-performance certified solutions.
Thank you, Anton. Now, while Anton reviews the questions that came in, I just want to briefly mention some of the additional products that we offer here at Epec. For more than 70 years, Epec's designed and manufactured custom build-to-print electronics. Our expertise not only lies in custom battery packs, but also printed circuit boards, flex and rigid flex PCBs, overmolded and other types of cable assemblies, CNC machining through our sister company Metalcraft Machining, high reliability user interfaces, flexible heaters, and energy efficient fans and motors. Next slide, please. And now we'll turn it back over to Anton to go through some of the questions that came in.
Yeah, I'm getting some questions here. Let me go through the first one. How do you know what type of cell to select for your project? Well, you have to determine how much capacity and voltage your device is going to require to include what the device will draw in current. Different types of cells have different capacities and discharge rates, so cell form factor will need to be considered so you can design a pack within the dimensional space constraints you have. Here's another one. How do you determine when the battery should be charged if it's not being used or been in long-term storage? The answer to that would be all chemistries really self-discharge, and the BMS on the battery is going to typically draw some milliamps. So the rule of thumb is to charge batteries when you receive them if you can. If you have to store long-term, keep the batteries at approximately 50% state of charge. Check them every 6 months to verify voltage levels, and charge again if required. Let me see, here's another one. How do you determine what type of material will be required for an enclosure? Okay, so there's many options, such as polycarbonates and ABS, aluminum, etc. It all varies depending on environmental conditions, the weight of the battery pack, and aesthetics. So, you have to work with your marketing team as well, as far as how you want that enclosure to look, and factor in how heavy the battery is going to be, etc. Here's another one. How do you plan, excuse me, for controlling thermals in the battery enclosure? So the design of the enclosure should allow for heat to dissipate somehow by having some spacing in the enclosure, maybe spacing between the cells if you can manage it. It could be designed with vents if the application allows, if it's not IP rated. There are some advanced thermal interface materials that help dissipate the heat away from the battery. And some enclosure designs even incorporate cooling fans if the battery is anticipated to get hot during charge and discharge cycles. There's a lot of options, actually. Here's another one. Can Epec certify battery packs for other customer or companies? The answer is no. We don't do that. Epec only certifies the batteries we design because the certification process is based on how the electrical is created, excuse me, as well as the enclosure. Certifying after the battery is already designed and locked in poses a risk to fail if the design requirements haven't been met. So we only certify the batteries we design and support. And here's another one. This is the last one I see. Do all battery packs need a BMS to control the charge and discharging? And the answer to that is the BMS is mainly for lithium batteries, but we have some nickel batteries designs that, nickel metal hydride, that use a BMS. And you got to keep in mind that all battery packs all lithium require a safety protection as a minimal to be able to pass UN 38.3. So not all battery packs require BMS, but lithiums to manage and get the most out of the life cycles, it's definitely required. And that was the last question I had. If you mail in more questions, we'll be sure to get and answer them via email in a timely manner. And I want to thank everybody for joining. I hope it was beneficial, and keep the questions coming.